All right, hello class. Mr. Pettibone here with bugs. Um, Unfortunately, Bugs isn't feeling very good, and I'm having a hard time figuring out what exactly is upsetting him. But he keeps making yip noises like he's in pain at just random times. So, like in the middle of the night last night, he just started basically crying like he was in pain, and I've been poking him and prodding him and trying to figure out where is the spot that hurts, and I just can't figure it out. It's like nothing hurts him, and then sometimes he feels fine. Um, but yeah, he's just very clingy today. He just wants to be right next to me, and so I think I'm going to do the lesson with Bug right here, um, if he lets me. So, all right. Hello, Alex. Hey, Mina. Hey, Mo. Hey, Luigi. Hey, Nick. Welcome. All right. So, I hope you enjoyed the 2004 free response mechanics. That was the one that I took when I was in high school. And today we'll be working on the 2005. Hey, Alex. We're working on the 2005 free response question. So let's get right to it. And I'll tell you what, I thought that from yesterday, the lesson, the free response was really quite simple. All right. So we're on number 1 here. And it says a ball of mass m is thrown vertically upward with an initial speed v naught. It experiences a force of air resistance given by F equals minus kV, where K is a positive constant. The positive direction for all vector quantities is upward. Express all answers in terms of blah, 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 blah. Does the magnitude of the acceleration of the ball increase, decrease, or remain the same as the ball moves upward? So as the ball moves upward, if we think about it, we've got the weight force going down, okay? And then we've also got, because the ball is moving upward, we've got the drag force going down. So we've got mg and we've got drag both going down. Now the higher up the ball goes, look at Buggy's just totally like resting his head on my arm. The higher up the ball goes, the slower it goes, and so when it's up higher, the drag force is going to be smaller, which means we have less of a downward net force. So I would say that it decreases because the net force goes down as it goes higher. Okay? Right, but do not solve a differential equation for the instantaneous speed of the ball in terms of time as the ball moves upward. So as the ball moves upward, we've got net force equals ma. The net force, as I said, is weight, force, and drag. So we have minus mg minus kv, and that equals m. I'm going to write the acceleration in terms of velocity. Okay. So there you have it. Oh, we got some more people. Hey, Salma. Hey, Alex. Hey, Justin. Hey, Aisha. I might turn this lamp off. Does that make it easier to read? Okay. C. determine the terminal speed of the ball as it moves downward. So as the ball moves downward, so here's our differential equation. Now, eventually the ball is going to reach terminal velocity, okay? And so once it's reached terminal velocity, the velocity isn't changing anymore. And so the acceleration becomes 0. And I'm not happy with how this is. It's like saturated. So that becomes 0. So we have minus mg minus kv equals 0, which means that v equals minus mg over k. So the terminal speed is going to be mg over k. Does it take longer for the ball to rise to its maximum height or to fall from its maximum height back to the height from which it was thrown? I'm going to say it takes longer to fall. Okay. So why do I say that? I say that because air resistance is taking energy out of the ball. Okay. So basically, when it hits your hand, you throw it up and it comes back down. When it hits your hand, it's going to have less of a speed than you threw it up with. And the reason is that air resistance took energy out of the ball. So because it ends up with a lower speed, it's got to take longer to come back to you than it did to go up in the first place. So I'll say it took longer to fall. On the axes below, sketch a graph of velocity versus time for the upward and downward parts of the ball's time of flight. Okay, so I guess I'm going to sketch this one, so I'll sketch it directly on the diagram. Okay, so the velocity starts out positive, and so we know that the velocity as a function of time looks like an exponential decay, so it's going to look something like this. Oh my gosh, I totally messed that up. Oh, that looks okay. Maybe if I stretch this. Try and make this look like an exponential decay. There we go. It's going to look like an exponential decay. So the highest point would be right here, because that's where the velocity is 0. And then, of course, this area under the curve would have to equal this area under the curve, because it goes up the same amount as it comes back down, and then it should look like an exponential decay. All right. So, moving on to number 2. Oh, this sweet boy. Look at this sweet boy. Oh, bugs. Poor guy. Is there a little doggy outside? Oh, I can tell you a story about Hazel. Hazel swallowed a lizard whole yesterday. She literally saw it. I pointed it out to her because her eyesight isn't that good. And I said, Hazel, lizard. And I pointed at it. And normally she can't see things that I point at. I'm like, lizard. I could be like, lizard right there. And she would be like, what? Where? But she saw this lizard. and the lizard froze instead of running, and she just went, and it was gone. No chewing, just swallowed it whole. It was pretty cool. I thought she was going to throw up a whole lizard, but she didn't. She digested it. All right, a student is given a set of orbital data for some of the moons of Saturn shown below and is asked to use the data to determine the mass of Saturn. Assume the orbits of the moons are circular. Alrighty. Write an algebraic expression for the gravitational force between Saturn and one of its moons. All right. So that would be G mass of Saturn times the mass of the moon over r squared. That's a really simple question. Use your expression for part A and the assumption of circular orbits to derive an equation for the orbital period t as a function of the moon as a function of its orbital radius. So net force equals ma, and we're going to apply this to the moon. The acceleration, the moon is moving in a circle, so it's the centripetal acceleration, which is 4 pi squared r over period squared, is one of the expressions. The net force is the gravitational force, which would be big G, mass of the satellite, mass of the moon over r squared. Mass of the moon cancels out. And then we can cross multiply and we get G mass of Saturn period squared equals 4 pi squared r cubed. Okay? Oh, Boogie. Oh, poor Boogie. Oh, you sweet boy. You want to lay down? Oh no. Did you guys hear that? That's what he keeps doing. He just keeps... Poor guy. You okay? Just... Okay. So, we're on part C. Which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass? So we have Kepler's law. I'm going to rewrite it in the form r cubed equals G mass of Saturn over 4 pi squared t squared. Okay, so you can see that if I put r cubed on the vertical axis and I put t squared on the horizontal axis, I would get a straight line, and the slope of that would be G mass of Saturn over 4 pi squared. Okay? So that's what I want to graph. D, complete the data table by calculating the two quantities graphed. So basically, I would calculate r cubed here, and I would calculate period squared here. I'm not going to do that because that would just take a lot of time, and I don't want to. Plot the data on the axes below. So I would have r cubed here, and I would have period squared here. And then it would look like a straight line. Oops. It would look like a straight line, which I would then calculate the slope of. So basically, so I did part D. We'll just say I did part E as well. And then I would calculate my slope, and I would get some number. And then I would set my slope equal to g times the mass of Saturn over 4 pi squared. Okay. So basically the mass of Saturn is going to be slope times 4 pi squared divided by g. All right. Question 3, it looks like it's a physical pendulum. Maybe a physical pendulum mixed with a collision, it looks like. It says, hey, James. It says, a system consists of a ball of mass m2 and a uniform rod of mass m1 and length d. The rod is attached to a horizontal frictionless table by a pivot at point P and initially rotates at an angular speed omega as shown above left. The rotational inertia of the rod about point P is 1/3 m1 d squared. The rod strikes the ball, which is initially at rest. As a result of this collision, the rod is stopped and the ball moves in the direction shown above right. Express all answers in terms of m1, m2, omega, d, and fundamental constants. Part A says derive an expression for the angular momentum of the rod about point P before the collision. We learned an expression for angular momentum. It was I times omega. The I value for the rod is 1/3 m1 d squared. So that would be the answer. Okay, that's really easy. Part B. Derive an expression for the speed v of the ball after the collision. So this would be a problem where angular momentum is conserved. Okay, so basically the initial angular momentum is carried by the rod, and the final angular momentum is carried by the ball. So the initial angular momentum is 1/3 m1 d squared omega. The final angular momentum is the angular momentum of the ball. Now, if you have a tetherball-like object, the angular momentum is mv perp r. So the mass of the thing is m2, and then the distance from the pivot is just d. So r is replaced by d, and I can solve for v. I get v equals m1 d omega over, so that cancels with that, over 3m2. So that would be your final speed. Assuming that the collision is elastic, calculate the ratio of m1 over m2. So I'm assuming that the initial ratio is, or the initial energy is rotational kinetic energy, so 1/2 I omega squared. And then the final energy is 1/2, it's the translational kinetic energy of the ball. Okay. So we have 1/2 m2 times the velocity of the other one squared, which would be this quantity squared. So we have m1 squared d squared omega squared over 9 m2 squared. So we can see the d cancels out. The omega cancels out. The 1/2 cancels out. The this m2 cancels that squared. This m1 cancels that. So what do we have when all the dust settles? We have 1/3 equals m1 over 9 m2. Then multiplying both sides by 9 gives us m1 over m2 equals 3. Okay? A new ball with the same mass, m1, as the rod is now placed a distance x from the pivot as shown above. Again, assuming the collision is elastic, for what value of x will the rod stop moving after hitting the ball? So we're going to have angular momentum conservation, L initial equals L final, and it looks like we're going to have energy conservation. So the initial angular momentum is I, 1/3 m1 d squared times omega. The final angular momentum is m1 vx. So the difference is that it's not hitting at the end of the rod, it's hitting at position x. Okay? And then we are also going to have kinetic energy conservation, so K initial equals K final. All right, which says 1/2 I omega squared equals 1/2 m1 v squared. Okay. So we can see that the m1's cancel. All right, here the 1/2s cancel. So on this equation becomes d squared omega squared over 3 equals v squared. And then this equation says d squared omega over 3 equals vx. So now I want to put in some geometry, okay? So remember how omega equals, or actually, I'm just going to take, maybe I don't need geometry. I'm just going to take the square root of this. So that gives me d omega over square root of 3 equals v, which I will then plug in here. So I have d omega over root 3 times x equals d squared omega over 3. Oops, sorry about that. You guys couldn't see that. So then omegas cancel, one of the factors of d cancels, multiply that over, and I get d over root 3 equals x. Okay. Man, I'll tell you what, guys, these mechanics exams are way simpler than the E&M. Maybe you guys think the same thing. All right. Well, that's all I have for today. I hope you guys have a great weekend, and I will talk to you on Monday with 5 more free response for mechanics. Then you guys should be prepared for the AP exam if you're taking it. And then after that, I might post a straw poll today on the Discord to see what you guys want to learn next. And then we'll go from there. All right. Have a great afternoon. Have a good weekend.